Thanks for the introduction, Karthik. As you said, my name is Ronak Buch. I'm a PhD candidate in the Parallel Programming Lab here at Illinois. I'll be talking about recent developments in dynamic load balancing. And this is joint work with Kavita, Juan, and Eric, all other PPL members. So just a brief rundown of what I'm going to talk about. First, we'll go through an introduction of load balancing and sort of what we've been doing recently with it. Then I'll talk a little bit about topological strategies we have recently, some performance improvements we've made to the load balancing framework, a new load balancing framework that we're doing for various reasons that I'll discuss later on, some improvements in heterogeneous load balancing, some miscellaneous changes, and then finally I'll wrap up with a summary. So I think you guys probably all know this already, being at the Tron workshop, but I'll go through a brief background just in case. Load balancing is a very, very key important feature of Tron++. It's integral to achieving scalability and performance, especially on modern machines. There are two main thrusts that we use when we talk about load balancing. One is improving the performance of computation. So to do this, we have to do a couple things. We have to minimize the maximum load of compute resources themselves, and this also improves resource utilization. Our other big thrust is to improve the performance of communication. On modern machines, the network is often a bottleneck, and we want to address that with load balancing as well. So to do this, we place communicating objects near each other. By near each other, we mean on the same physical node or nearby topologically. And we do this to minimize network load. And our end goal is basically to improve application execution time in general. And these two things are the main components of that. So there are a lot of challenges that we've encountered recently in regards to load balancing. One is that we're getting very, very large machines now, and they're only going to get bigger as we look at future machines that will come online. So we have hundreds of thousands of cores. We've done runs over millions of cores before, millions, if not tens of millions of objects. So these problems are getting bigger and bigger. One of the big issues here is that if we strong scale a problem, the amount of work per core goes down, but the amount of load balance effectively stays the same. We're getting more cores and more objects, but less computation. So load balancing becomes a bigger and bigger thing as we do this. So in order to address this, we need to reduce the cost of load balancing. This involves a few different factors. One is collecting statistics. So to do load balancing, we collect some information during the run, we pass it to the strategy, and then we migrate objects. So our first thrust is fixing the efficiency of statistics communication. Another big thing is that comm-aware load balancers, which are often used to be cognizant of the communication in the system, requires the collection of comm statistics, but they're expensive to collect and expensive to use in strategies. Another big one, like I said before, is running strategies themselves. Now that we have so many objects and so many cores, the logic of actually just running through and mapping things can take a long time. Finally, we have to migrate objects. There are two ways we can fix performance problems here. One is by moving fewer objects in the first place, and the second is moving objects either within the same node or nearby topologically, because that's cheaper than moving them somewhere else. And ideally, we would just not move them at all. So in order to address these things, we're working on a few different things in Tron++. So we have new strategies aimed at preserving topological mapping. We have performance improvements for existing load balancers. We have, like I said before, this redesign of load balancing framework, new load balancers for heterogeneous systems, and a few other miscellaneous features. So first, I'll talk about the topological strategies that we've added. So we've added a new strategy in Tron++. It's called Diffusion LB. And it's a distributed graph refine-based strategy. Essentially what this is, it's a neighbor-based diffusion, and it tries to retain the partitioning of the communication graph. So I'll go through the strategy and show some diagrams, and hopefully it'll make more sense after that. So the strategy itself is as follows. Each node finds its neighbors in the topology using a feature of Tron++ called Topo Manager. Then each PE on the node sends its local load statistics to a representative PE on the node. These representative PEs on each node communicate with each other. They share their load stats, but only with their neighbors. They don't do this globally across the entire job. Then each neighbor PE sends and receives object load tokens, which represent the loads of these different objects, until they reach a stable state where load is balanced across the entire job. Then we actually perform load balancing after this token passing stage is completed. And since the load is transferred only to neighbors, the communication cost increased by up to a single hop per LB step. Since we communicate to neighbors, they communicate to their neighbors, and so on. So here we have a graphical diagram of what this actually does. So here you can see from steps 1 through 5, we slowly move work over from neighbor to neighbor until we get a balanced state here in step 5. So it's a diffusion-based scheme. It happens iteratively. It goes through multiple iterations to find the stable state. One key thing is that we avoid non-neighbor communication, so we know that everything we do is basically going to be one hop away. And we do same-step diffusion. Once the tokens have been exchanged, we perform load balancing and move on to the next step of the algorithm. We use some other things to make this communication aware. So we do something called gain value computation, where for each object in a node, we compute a gain value associated with its communication properties. And it uses some properties of the owner node and the neighbor nodes in the job. Then we use a heap of gain values of objects. We get the object with the minimum gain value. And sometimes we take into account the gain values of neighbors. And once it's set to be moved, we update all the gain values of other objects in the node. So you don't need to worry about the logic so much, but the key thing that we're trying to do here is keep heavily communicating objects on the same node. So here's an evaluation we've done with the strategy. So here we use a regular k-neighbor with one modification. Rather than communicating to just your neighbors that are one away from you in terms of objects, we vary the strides. You could be communicating with everyone that's 4 away from you in each dimension, for example. So the key thing here is that objects with low within node communication are more amenable to be migrated during load balancing. If you're communicating 8 away, then your gain is going to be lower. This is with 64 nodes using 8 cores on Blue Waters. Diffusion LB is the short bar here in the middle. And you can see that it minimizes communication, and because of that, it minimizes overall execution time. Another strategy that should perform similarly to this, Metis, which is the bar right next to Diffusion LB, for some reason results in high communication, and we're not really sure why that's happening yet. That's currently a topic of exploration. The other really good thing about this kind of strategy when you use neighbor communication is that it's very scalable. We don't have global communication. We're only communicating to neighbors. So it's really, really effective for large jobs. Next, I'll move on to some of the performance improvements we've made. So we've done a lot of different experiments across the stack for load balancing, but a lot of these have been sort of ad hoc and not generalizable. We're doing these just to figure out what works, what doesn't work, test some hypotheses. But we're using all these things we've collected to redesign the new load balancing framework, which we'll talk about in a few slides. And that'll actually provide the benefit that we observe on these experiments to all the strategies. So I'll talk about one of these aspects in particular, an experiment called Fast Central LB. What this does is optimize all phases of centralized load balancing. So stats collection, the load balancing algorithm itself, and then sending migration decisions. One of the big things that this does is it makes the stats and migration messages much, much smaller than what they were before. And since they're smaller, they take less time to send. Currently, this only works with greedy refine and its variant topo greedy refine, which we'll talk about later on. But we see observed speedups compared to central LB, the original central LB plus greedy LB of 4 to 7 times. So here are some results. So here, this is stencil 3D. So it's sort of a not imbalanced program to begin with. So we're not really caring here how good the load balancing quality is. We're caring how long it takes to run. This is 4 processors per node on Blue Waters, and then 7 worker threads per process. This particular run is on 1K nodes with 29,000 PEs and 229,000 objects. So we see here that there's a very big difference between greedy, which is essentially the current way of doing load balancing in Charm, and greedy refine, which uses, in this case, the new fast central LB. Dummy, in this case, basically does nothing. It does stats collection, but that's it. And we see here, in this case, probably just due to noise, topo greedy refine is actually slightly faster. If we look at an even larger case, this is, again, the same machine, same benchmark, but now 4K nodes, 115,000 PEs, and almost 1 million objects. We see that greedy is now much, much slower than greedy refine and topo greedy refine. So these improvements, we're going to be making it into the new LB framework when that's released. Speaking of which, I'll go into some more details about that. So first, some background. The existing load balancing framework consists of a few main components. So we have a database, which consists of the LB database, the LBDB manager, another component called the LBDB. There's something else called the meta balancer, the central LB and base LB, and all of these are basically base classes for load balancing strategies themselves. But one of the big issues is that there's no real clear delineation of responsibility across these entities. So stuff from the LB database works with stuff in the LBDB. Some of the logic is pushed to the central LB, some logic is pushed to some other helper files, and it's all sort of complicated. And a lot of this is just because the system has been around for a long time, and a lot of people have worked on it, and it gets more and more corrupt as things age. There's a lot of unnecessary duplication of data structures. Like I said before, a lot of the core logic shows up in strategies themselves, which makes it really hard for end users to write their own strategies, and it complicates things that should just be mapping algorithms into these big structures where you have to do a lot of things that shouldn't be necessary. And very little of the API here is actually accessible to the application. So what are the problems with this current framework? One of the big issues is that strategies can't easily be run with different metrics. So most strategies are agnostic of the semantics of the data. If you write a greedy way to assign objects to processes, the greedy load balancer doesn't care that the values it gives to you are actually what CPU load is. You could give it size, you could give it GPU load, you could give it a bunch of different values, and the algorithm is going to perform the same. It has no dependence on what the actual values mean. Additionally, strategies can't be run on arbitrary domains. If I want to run a strategy on just a single node or just a certain rack, I can't really easily do that with Charm right now, and there's no reason why we shouldn't be able to. There's a lot of duplication of data in tracing and load balancing that currently just exists as performance overhead and makes the code harder to manage. Like I said before, one of the big issues is that strategy logic isn't well abstracted from the LB infrastructure. So if you want to modify the way that load balancing happens, you have to end up modifying a lot of strategies as well, which should be decoupled in essence. Statistics collection isn't really that flexible. If I want to add a new field to what's collected, it's hard to do. And it's hard to control the load balancer at runtime. I can't, for example, easily run a new load balancer dynamically. Say I suddenly decide I want to do refine and insert that into the list of load balancers. It's a difficult thing to do right now. So we've decided to make this new load balancing framework. Here's the high-level sketch of the way it looks right now. We've made some isolated components. So we have LB Manager, which is responsible for interfacing between the application, which is what the users would actually be writing, and the rest of the load balancing framework. The database is now purely a database. It doesn't have any logic like the previous version did. And Meta Balancer, which is responsible for some things about selection and basically running how frequently and what runs in the load balancer, is now a fully separate component rather than being entangled with everything else. So a lot of this is just really relevant to internals developers. But the key takeaway here is that things are going to get simpler and things are going to get a lot more flexible for end users. So currently, this rewrite is in progress. We expect to release something later this year. All these issues we addressed, or I talked about earlier, should be solved by this new rewrite. The performance improvements that I talked about before, like fast central B, are all incorporated in the system. It cleanly separates everything, as I've said before. The way that we've architected things is intended to make things easy to orchestrate and easy for end users to manipulate. And one big win is that writing strategies has become a lot simpler and more concise. So for example, greedy has gone from around 157 lines of code to 22. And that's one of the simpler strategies. Just as a showcase of what it actually looks like, this is an excerpt of one of 3 files that exist for the current greedy load balancer. This is about half of one of the files. And this is the entirety of the new greedy load balancer in the new framework. So even like half of this is basically boilerplate. So it essentially distills down to something very, very easy to write. You just have to write a mapper from objects to processes, and that's it. Like I said before, one of the big things are the strategies in the new LB framework are now very abstracted away from what values they actually get. So rather than needing objects to be objects or needing processors to actually be processors, the infrastructure can lie to the strategy and replace them with whatever it wants to. So for example, if you are agglomerating work from multiple chars to run on a GPU, you can present all of those chars as a single object to load balancing framework, and it can move that around as an atomic unit. So we can now put these strategies on any level of a hierarchy, as long as they deal with generic objects and generic processes. You can still make load balancers that deal with specific things that the load balancing framework won't lie to you about, basically. But it gives you more flexibility, and it lets the strategies be used more flexibly. Tying into what I said before, there's also a redesign of the hierarchical infrastructure for load balancing. So this, again, replaces the current central LB and hybrid LB infrastructure. The big thing here is it's pluggable at each tree level. So the existing one is sort of rigid in the way it works. Now you can put any strategy that is centralized into the tree. Each tree level can aggregate stats in a different way. So we have a strategy and something that we're calling an LB mode for right now that's responsible for the logic of how things in the tree interface with the strategies themselves. And a big benefit here is that you can create basically arbitrary hierarchies. So you can say you want to make a 4-level tree of cores, processes, nodes, and the entire job. You can do that. And all the strategies that exist in Charm are ones that you write yourself. We'll just work with it. So it should be a big shift. We're hoping that's going to have a lot of benefit for end users and for people who work on Charm themselves. But if you have any questions for that, please talk to one of the load balancer developers after this talk. The next thing is heterogeneous load balancing. So a little bit of background. The big thing is machines are getting really diverse now. Lots of machines have CPUs, GPUs, things have Xeon Phis, although that's kind of dying out a bit. But the big thing is a lot of these flops are coming from non-CPU devices. And as the NAMD talks earlier illustrated, without cognizance of what's running on the GPU, it's hard to get good load balance. So the standard CPU load balance we have in Charm++ isn't really sufficient for all of these things. But there are a lot of challenges we're facing in this area. How do we balance a lot of metrics all at the same time? How do we actually measure load on multiple devices? How do we account for things like data movement and placement and all of those things? There's also some programs that have CPU and GPU only work, whereas others may have work that can be executed anywhere. And some may have a mix of all of these things. So the problem is very complex. And we're addressing it in a couple different ways. So we have a few experimental versions of heterogeneous load balancers already. We have two main paradigms. So we have one called vector load balancing. And what that essentially does is it's intended for applications that have separate CPU and GPU portions. And instead of creating a single value for the load, it creates a vector for the load. Then we use algorithms to balance across that entire thing. There's also something else called Excel load balancing. And that's mostly used for applications that have work that can be dynamically targeted. So if I have a particular routine that I could run on the CPU or the GPU, it'll figure out where to run it using some metrics, and then actually run it there. And it'll use runtime information to figure all these things out. So neither things are really production ready yet. We're working on making them right now. Ideally, they'll be released with the new LB framework that I talked about before. Another thing is we're adding load balancing measurement to the GPU manager, which you'll probably hear more about in their talk tomorrow, so I won't discuss that here. A little bit more detail about vector load balancing in particular. So rather than using a single value, like I said before, we use a vector of different load metrics. So for example, we could have things like CPU load and GPU load. Or for an application with a complex iteration, we can have phase 1, phase 2, phase 3. Different dimensions may have different optimization. We may want to minimize some. We want to maximize some. We may want to hold some below or above a certain threshold. We can incorporate all these things into this framework. One thing, like I said before, with these phases, is not necessarily just for heterogeneous hardware. If you have an application that, for example, half of the objects do something in the first subphase, the other half of the objects do something in the second subphase, the regular load balancing framework would look at those two and say they have the same amount of load. But really, we want the first phase and the second phase to be equally spread across the machine. So this lets you specify those intricate details about how the application actually runs. So the big thing here is we need to change the strategies to now consider the dimensions of these vectors while making decisions. So we've implemented a few new vector load balancing strategies. So here are a few of the different algorithms we have right now. There's one called greedy max LB, which is very simple. Essentially just takes the vector and gets the maximum and uses standard greedy assignment to figure out where to place things after that. There's another one called multi-greedy LB, which uses a separate heap for each dimension of the vector and greedily assigns them. It's a little bit difficult to understand and explain, but it's different from greedy max LB because rather than mapping to the P with a minimum value for the object's highest load dimension, that's what that does. And in the greedy max LB, it maps to the P with the smallest maximum value globally rather than the one just for its dimension. So it's a little bit difficult to understand, but the takeaway here is multi-greedy LB is better. And then there's also greedy norm LB, which instead of using just a maximum of a vector load, we calculate some norm based on the current vector and try to minimize some vector norm when we place objects. Here are some results. These are all experimental, so don't take away too much from them. But these are this is null LB over here, greedy max LB, multi-greedy, and greedy norm LB. The key thing, so the object, the box is the range of at each process. So the x-axis and y-axis are the 2 dimensions of the load vector. And each point is a process, and its position on the x and y is its load on that particular dimension. So the key thing we care about here is minimizing the top right corner. The top right corner is where we have the most load in the x and y dimension globally. So as you can see, when we move from null LB to greedy LB to multi-greedy to greedy norm LB, the top right corner moves down and to the left every time. And also the variance, which is the full range of this box, decreases every time. So what we really want is greedy norm LB, but there are some questions still about which one is the best to use in practice. And the reason why these questions show up is because of the performance of the strategies themselves. So null LB is obviously very fast. Greedy and multi-greedy LB take about the same time. Greedy norm LB is like 36 times slower. These are all in simulation. These aren't in an actual charm run. These are a separate load balancing simulator that we made. But we still have to figure out these trade-offs between the balance, quality, and performance. Finally, a few small topics. So Meta Balancer is a system that we have right now in Charm++. Currently, it uses a machine learning model. We have a random forest that we trained fully offline. And it uses this to automatically select the optimal load balancing frequency for an application. One thing that we're adding right now is automatic selection of a load balancing strategy. So rather than just figuring out how frequently we want to load balance, we want to figure out what load balancer we should run whenever we do load balance. Another thing we're changing is that currently the model is pre-trained and fixed to a certain set of load balancers, and we ship this model with Charm. But if you want to write your own load balancer or you want to retrain this model on your own system, you can't do that right now. So we're trying to figure out a way to let users actually train on their own systems, on their own applications, by their own metrics, and for their own strategies if they want to make their own. Topo Greedy Refine is an extension to Greedy Refine, which I talked about extensively in last year's LB talk, so I won't go over it again. If you are interested, go look at the slides from last year. Basically, it's a version of Greedy that constrains the number of migrations that are made. This one in particular constrains them even further to some local topological neighborhood of where they currently are. So rather than just trying to minimize migrations, we want to minimize migrations and make sure they stay somewhat local. That is also going to be released with this new load balancing framework. Finally, distributed LB. This is our gossip-based probabilistic load balancer that Harsh worked on a few years ago. We've modified that a little bit to now do migration decisions in multiple phases. The big takeaway here is, since this is probabilistic, earlier, every single process had the same probability that it would migrate to an underloaded process. Now we prioritize overloaded PEs, so it's much more likely to get a good load balance now. So just in summary, we have new topological diffusion strategies. They're really optimized for communication costs and scalability, and we've shown that they work well in particularly minimizing communication. There have been a lot of performance improvements in the LB infrastructure. Unfortunately, a lot of those aren't shipping in the current version of Charm, but they will be included in the new load balancing framework, which will improve performance, hopefully usability, flexibility, applicability, and give us a good baseline for future load balancing research. Finally, heterogeneous load measurement and strategies are trying to address the CPU-GPU issues that we've been seeing in a lot of applications and other complex imbalance. And that, again, should also come with a new load balancing infrastructure. So that's all I have. Are there any questions?
I don't know if you've ever looked at the multi-step LB that I use in Changa.
Yeah.
So, well, frankly, I'm not very happy with it. I mean, it's got its issues. I mean, have you thought about using your phase-based strategy to replace that?
Very much so, yeah. So it's currently not production ready, and we're still basically trying to implement it to work well with the new. One of the big issues is the new framework's not completely ready yet. It runs, but it's not super applicable to most applications just yet. and it relies on some features of the new framework to run. So it's a bit difficult to get it running with something like Changa right now. But that was one of the motivations, in fact, for this new load balancer was Changa specifically. So yes, very much so.
Okay. Looking forward to it.
Good.
You probably already said this, but I just want to make sure. This will address David's question about GPU-aware load balancing when it is done. True?
Well, yeah. So to go into details for NAMD right now, it will not, because NAMD doesn't use Charm's GPU framework. But assuming that does work, then yes. Assuming if NAMD switches to using our GPU framework or supplies data into this framework, then yes, that's one of the intentions is to address things like that.
Alternatively, we modify the NAMD load balancer to use the GPU measurements in any case. Yeah.
Right.
Okay.
Right.
But I guess I understand the point about vector balancer. NAMD will have to switch to using this for that. Okay.
Right. Exactly.
Got it.
Thanks.